I would like to introduce you to Professor Krister Sundblad. He's been a professor in several universities in Norway, Sweden, Finland, working on mostly in the Ferroscandinavian Shield in our deposits. And he's going to be talking today to us about this interesting research subject about the metallogeny of indium in the Svecofennian domain from the Northern Europe. So basically, this is in the southern part of Finland. Okay, so with no more delay, I will let our guest to give his talk. Thank you very much.
Green light. So, being in these parts of Europe, we have Phanerozoic sediment or sedimentary rocks everywhere from Cambrian into Mesozoic, which are covering the Precambrian. Oops. Oh, I get on thin ice. How to get out of this now. There we are. So if you would put a drill machine somewhere here, you will find Precambrian after a few hundred meters or a kilometer or two. But if you put a drill machine here in Barcelona, you need to drill very far. The next Precambrian you might discover will be in Australia or China. So it's a very important line here where everything here is the East European platform. Precambrian rocks covered by Phanerozoic sediments or exposed Precambrian rocks. And this is the Fennoscandian shield, which is the biggest exposed piece of Precambrian in Europe. Even better resolution of it, you can see that it's surrounded by Phanerozoic sediments in Denmark, Baltic republics, Russia, and even in the west, it's covered by Caledonian rocks and a thin sliver of Cambrian sediments. So this is the shield in the bright reddish brownish colors. And you can also see how we can subdivide the Fennoscandian shield into various units, where the northeasternmost parts, mainly existing in Russia and in Finland, these dark brown colors, they are the Archean rocks, more than 2,700 million years. They are followed by so-called Karelian rocks, supercrustal rocks at about 2,200 million years. So they are the first expressions of Proterozoic rocks. And then we get into a major part of Fennoscandia. We call it the Svecofennian Domain, and that is one of the words I had in the title of this talk. They are rocks which are formed in a very short time period, close to 1,900 million years, existing in southern Finland, partly in Russia, and constitute a major unit in Sweden. We have a slightly younger unit in the southwest. We call it TIB, the Trans-Scandinavian Igneous Belt, followed by even younger rocks in the far southwest. It's simply shortened as Southwest Scandinavian Domain, where we get almost into the Phanerozoic age, almost. And then, of course, we have the Caledonites, which is a Cambrian-Ordovician-Silurian complex. If we continue with the details, I will definitely talk more about the Svecofennian and not the least the Trans-Scandinavian Igneous Belt. Yeah, one more thing about what we saw in this picture. Remember carefully the Karelian crust up here and the Svecofennian. That is metamorphosed crust of whatever, volcanic, intrusive rocks, sedimentary rocks, but they are metamorphosed and deformed. It's you can write books about this area, but it's also from a ore deposit point of view, the most important of Europe. There are so many mines, existing operating mine of world-class style in Finland and Sweden, making this area as the most important mining region in Europe. We have up in the north, world-class iron, world-class gold, world-class nickel. We have copper, zinc. We have copper, zinc, lead in that part. And up here we also have chromium and nickel existing also here, and gold in the extreme east of Finland. That's an interesting corner of Finland because that's also the absolutely easternmost part of European Union. I think Josip forgot to mention that I have had many Spanish students. In my last 10-15 years, we had lots of Spanish students coming on Erasmus contracts up to us in Finland. And interesting enough, they didn't just come for studies. They found Finland and Sweden an excellent place to be at. So I still have two of my former Spanish students. They are now working. Here is one of them. Diego is working just a few kilometers from the Russian border, and he seems to survive. And then we have David Garcia Balbuena working here as a chief geologist in one of the major nickel mines. I have very close contact with these people still, so it has been a very important part for me to join these Spanish students, regardless whether they are still in Finland or if they are in Madrid or elsewhere in Spain. I have met several of them on this trip. So this is an important part of the Fennoscandian shield. But when we talk about indium, that does not occur inside these metamorphic segments. The indium is related to later granitic complexes. And particularly, we shall focus on the so-called TIB, that is the Trans-Scandinavian Igneous Belt, extending from the Baltic Sea through southern central Sweden into Norway, where it disappears under the Caledonian Rust Belt. You can also subdivide the Trans-Scandinavian Igneous Belt into several generations. At least we have generations 0 and 1 down here. We also have slight expressions of 0 up here, but we also have a second generation called TIB2. And if we would go back for a while into this complex, we can say that seen from the ages here, Archean, early Proterozoic, mid-Proterozoic, Neoproterozoic, we have a younging system from northeast to the southwest. It's a constantly accumulating crust into a bigger and bigger continent, always related to subduction zones and collision of various units. There are, however, some expressions of continental rifting, and they are of most importance for the indium business. So if we go back now to where we have the important indium things, we are not focusing on the TIB rocks down here. They have no indium. But once when you go up to the TIB0 or the TIB2 in this yellow and light red colors, that's one place for the indium. And we also have these purple colored plutons of so-called Rappakivi granites. Rappakivi is a Finnish word meaning rotten rocks, simply because they tend to weather quite a lot. But sometimes you can even use Rappakivi as dimension stone, and I have seen it at several places here in Barcelona, proper Rappakivi, because it's a beautiful granitic type. And all of them, they are expressions of continental rifting, failed continental rifting, so it never created any new ocean. But from 1635, when the oldest of them was formed, the Viborg batholith. Slightly later was the Rappakivis on Åland, 1570. Slightly later we came to the Salmi batholith, and finally we have small examples like that one hidden under this red bottom. There we have one which is 1500 sharp. So we have several pulses of rift-related granites in the Fennoscandian shield or in the Svecofennian domain. In addition to these yellow-red areas there, which are also rift-related. So most of the TIB is subduction-related, but from these yellow-red into the Rappakivis, we have one and the same extensional regime, creating very high silica granites, which are also associated with hydrothermal activity and producing many, many metals, including indium. So, what is indium? To be honest, 30 years ago, I didn't know much about indium. I had seen it in the periodic table, but it was not until some 20 years ago I happened to be in Japan on a geological conference for a completely different purpose. I was working with volcanogenic massive sulfides at that time, and then I could hear that it was a large demand for indium, particularly in Japan, because they were more or less the single producer of indium. And now it was problems with that mine. So now they were looking for indium elsewhere. And that was where I picked up the message that indium has a big value. The metal as such, it looks like this. Could be silver, could be tin, whatever. I never touched the indium as such. But I understand that if you try to bend it, it doesn't break more than you hear this crispy sound exactly like you have with the tin. And that's what this beautiful lady is trying to express here. It gives a very specific sound when you happen to have it. But if you happen to have this, then you have quite a lot of money in your pocket. This is a very high price on the Indian market now, because it is what we need in the mobile telephones, in the flat screens, and many, many other electronic devices nowadays. So we have got to a situation where we didn't know about indium 20, 30 years ago, and now everyone is running around with telephones, the screen here, wherever, and we have an enormous demand of it in Europe, in North America, and all well-developed Western countries. And the producers, well, we don't even have production of it in Europe. We can produce whatever metals in Finland and Sweden. But so far, we have no domestic production. And now Japan is superseded by China. So we have got into a trap that the Western world needs metals that China has monopoly on. It's a really dangerous situation. So I jumped on that train directly after coming back from Japan 20 years ago. I knew where to look for. I saw the geological characteristics they had in Japan, and I started testing it in a few areas in the Fennoscandian shield. And it was full hit in both cases. I put priority. So I started looking for it. Just this picture to mention also something about the metal and the metal market. This is a picture from one of the biggest zinc mines in Finland, where this train is filled up with svalerite concentrate that they have taken up from the mine. And the knowledge 20 years ago was that indium is always connected to svalerite. So this was, of course, one place I needed to check how much indium was there, and it was close to zero. This is a volcanogenic massive sulfide, and that's useless, at least in Sweden and Finland. I know that VMS deposits can have plenty of indium elsewhere in the world, but not in Fennoscandia. So even if the zinc production is important, both in Finland and Sweden, this is not the meaningful areas to search for the indium. Actually, indium was discovered, first of all, the history of indium goes very much to Europe. Out of scale in this map, going down to Germany somewhere here, it was discovered for the first time ever in 1863 in the Erzgebirge of southeastern Germany. 1863. Almost 50 years later was the second discovery of indium. That was the Russian very famous scientist Vernadsky, who discovered it in this place. I call this place the Ladoga region. St. Petersburg is located down here, where he was a top scientist for many, many years in the late 19th to early 20th century. So that's the first discovery of indium in the Fennoscandian shield, and the second in the world. After checking this carefully 15, 20 years ago, I found that you can get indium in Fennoscandian shield in veins, quartz veins, alteration zones, hydrothermal alteration zones, or in skarns. And by the way, how many people in the audience know what language is skarn? It's an international word, but that is actually coming from Sweden. The first skarn deposits were described here some 150 years ago, and skarn is Swedish, and I happen to know what it means. It's a really, really dirty word, so I will not translate the details. So that was the word they used for the skarn ores for the first time, because the miners, they didn't want the garnets, the pyroxene, the aby-product, and that was just disturbing the metal production. So they said that this is skarn ore, and that was really bad word for those. Nevertheless, we have indium in the skarns, makes it better value, and in the alteration zones and in the veins. And we have them in almost every place where we have granites in an extensional setting, typical A-type granites in simple geochemical classifications. So taking them now in sort of a geochronological order, we go up to central Sweden, where we have several granitoids. We can call them Rätan granitoids, Dala granitoids, etc. And they are about, they range from the oldest Tib generation, 1850 million years, into 1617. So there are actually 2 generations of indium-bearing granites in this region. More details on the granite types, and you can see how I divided them into the Tib 0 generation. One of them, Kamptjärn granite, is the oldest indium-bearing granite, where we have very nice grays and alteration zones with reasonable indium grades. And the Tib 2 generation, millions of years later, Rätan, Dala, and Siljan, also very good traps for indium deposits. So the previous picture I showed was this granitic complex system with the Siljan, Rätan, Kamptjärn granites. And when you go into the white areas here, that's Svecofennian rocks, the old metamorphosed crust, which has a lot of metals of VMS type and other classical ore types. But we also have skarn types down here, skarn that is formed from the intrusion of these 1850 to 17 million year old rocks. The grades we are talking about is these grays and veins, up to 50 ppm, and then you get into the skarns, we have 100 ppm indium. It's not that bad, particularly since we have lots of other metals there. Here is one area of this extreme west of this Svecofennian mining province, where we have, you can see slightly an estimate of the number of mines here. That's the scale, 20 kilometers. So it's quite a big area, and it's spotted with iron ores. Iron ores are almost in every corner in this mining region. But some of them, particularly in this area, they don't only have iron. They can have chalcopyrite, they can have sphalerite, galena, many different silver minerals, even cassiterite. It's a very polymetallic region, and that polymetallic character is only here in the extreme west. If we go this far east, the polymetallic character disappears. So it's something with the rocks and the ores here that make them connected to the polymetallic A-type magmatism. There are some places in particular that I should mention. Långban, an extreme mineralogist would definitely recognize that one. Långban is one of the 2 most mineral-rich places in the world. You can, in principle, find any mineral there. I think 200 minerals have been discovered there, some of them uniquely for that place. Gåsborn is another one with lots of different minerals. And it's not a surprise that the first discovery of indium minerals in Sweden It was here in Longban. It was a British mineralogist who found the first rocky site there in 1980 or something like that. And all these places, they were key places for me to find, since I have heard a rumor that some indium should be here in Longban. Of course, it was found also in Gåsborn, and we have now several places here with good indium grades. Here I have listed some of these deposits. You see, first of all, the Longban and Gåsborn in those two lines, and you have others. This is a famous silver mine that was operated for hundreds of years. Others are more or less big in the mining history, but you can see I have all the types. Grays and veins in the granites, the real Tib granites, the skarn ores and the vein ores. Look at some of the grades. I put them in red. From Longban, you have very much copper there. You have at least also silver, and not the least some indium. 12 ppm is not very much, but in this particular sample that I put a star on here, that is the same sample that Burke and Kieft, that they were those people who first found rockysite in Sweden. So even with such a low grade as 12 ppm, they managed, by being extremely good mineralogists and using a microprobe, to find and identify the rockysite. Well, we can have many other aspects on these deposits. They may be very high in silver, tungsten, tin can also be high in some of them. And this is the polymetallic style. And what did we have for the indium? Yeah, they are never really reaching the 100. The closest is on Getön, but it's typical for Western Bergslagen or this skarn and vein types in Sweden. I think we should go further now. Yeah, that's one more about the 83 ppm, but I think we make a concluding thing that one Dutch team long time ago, they did a sulfur isotope investigation of these skarn ores, and this is particular for Josip and Abigail. That's the only publication we have on the sulfur isotope composition of some 10 different samples. They are from -4 to +1.5, which they concluded was a very uncontaminated granite. So this is a good guide for us when we are looking for sulfur isotope compositions in Finnish deposits. We are extremely similar to this figure. So we were just now in here. Now we move from 1670 rocks into 1640 rocks, and that is a proper Rapakivi batholith, the Viborg batholith. Viborg batholith is the biggest of the Rapakivi batholiths, and we are now also famous for the Sarvlaxviken site, which is here in the extreme southwest. And I'm very proud of Sarvlaxviken in the context that this map was presented by a Japanese team, Murakami and Ishihara, 10 years ago, where they tried to summarize all the important indium sites in the world. Of course, they have Bolivia as a very important center, and of course they are Japanese. They have lots of it in Japan, and putting Japan in the center of the world. But going to Europe, well, we have something in the Weber's Corvo on the border between Spain and Portugal. Getting up to the Erzgebirge here in Germany, the first indium discovery at all in the history. And the rest is at Sarvlaxviken in Finland. Very happy for that. Murakami and Ishihara said so in 2013, and they had apparently seen our first publication a few years before that, because that is the real place for indium in Fennoscandia. So this is how it looks. We go into the Viborg batholith. We are in the western, extreme western part of the Viborg batholith, just on the border to the Svecofennian crust. And we have another case up here, we call it Pyhäsaari. And looking at this, we can define several types. One of them is indium in connection to magnetite. Indium is constantly sitting inside the sphalerite lattice. It's not any crazy indium contents, 20, 30, 40 ppm or something like that. And it can be massive magnetite. Sphalerite can also be important, but if we would make money of ores of Pyhäsaari and Getmosmalmen, well, it would be some cents we would get for the magnetite. We would probably get some couple of euros for the zinc and something for the indium. So it's not very much, but still important that indium is always in sphalerite there, and it operates together with magnetite inside the granite. Sometimes the exposed Fennoscandian shield can be very difficult to find. It's a lot of soil cover. So one way of looking for this is by using magnetometer. Walking with like a backpack, a magnetometer, and having a GPS. This is a map done by one of my students some 10, 15 years ago, where this forest area had no single natural outcrop, but by carrying a magnetometer in this, it's about 1 square kilometer, she could identify 1, 2, 3, 4, 5 real zones, magnetic zones, linear shaped. And when we had the precision of the measurements, the peak of the magnetic signal, we knew that under us here will be a magnetite body. Yeah, we could even do it by hand digging or excavator digging, which we did last year, revealing really big magnetite sphalerite bodies. So that's some of the history for that ore type. Leaving that ore type, we go into proper quartz veins. We can call them Grayson veins, we can call them simply alteration veins, and they occur in many places, mostly around Sarvlaxviken, but we also have them in Jungfrubergen and Näseberget and all the way into Kymi. But this Sarvlaxviken, that is the place that Murakami and Ishihara saw all the beauties. They can look like this, simple alteration veins in the granite. And now the granite is not looking very much like a grappa kiwi. It's much more fine-grained, but it's also geochemically more evolved. And the veins here can contain lots of sulfides. In this case, they don't have the quartz, but they are just alteration. Looking at the metal contents in that kind of veins, you can see that zinc can be quite impressive. Also silver. And this case, the indium, is more than 10 times what we had in this magnetite association. Here is no magnetite at all. It's only the base metals, noble metals, and this indium. This would be a fantastic commodity to mine and sell, but you saw the veins. They're not big. So that makes them more of academic interest than for mining. If we go now to the proper quartz veins of Sarvlaxviken, we are getting down to a very small area here. Maybe we can see something of them, particularly here. This is the quartz vein And now you see it's a proper Rappakivi texture on the granite. And the chalcopyrite is definitely visible here. Same should be on this and the other sample, but this one is even better for the arsenopyrite. All the shiny gray minerals here, they are solid arsenopyrite. They're from different veins in Sundblad, and if you look at the grades, you get another dimension here. First of all, they are like this, 1,000 up to even 1,500. Some of them are much more modest, at least 146 doesn't look much compared to these, but it's still much more than we had in the magnetite association. Other metals are also quite good. The copper, the arsenic, and silver can locally be good, but also here, very, very thin veins. We have not seen anything better than this. From a microscopic point of view, it's an ocean of nice minerals you can recognize there. The copper is not only in the chalcopyrite, you have it in bornite, covaline, digonite, etc. You can get many, many other minerals in this association. But the absolutely biggest sensation here is that we get, besides from some minor sphalerite, we also get the mineral rockisite. That's the proper indium mineral, copper, indium, sulfur, a composition which is almost like chalcopyrite. If you just kick out the iron from the chalcopyrite and replace the iron with indium, then you get the rockisite. And that is the first rockisite discovery in Fennoscandian Shield, when we got this Sundblad. Thanks to my cooperation with Barcelona people, Abigail and Josep, we have now preliminary data on the sulfur isotope composition on these veins. This is the range we have documented so far. And if you remember what we had from Western Bergslag and Western Svecofennian, it's almost copy-paste of the same numbers. So I think it's very interesting that this system goes for hundreds of kilometers. So that was Viborg. Now we jump back to the west. We talk about the Åland. That is how we pronounce it. Åland is this island which is entirely built up by Rappakivi granites. This is where I had one of my Spanish students doing his master thesis there. So he has produced this map, not only the cartographia, it's also that he did all the walking, mapping, identifying this yellow Rappakivi system that was not detected before. And that is, as here's his name, by the way, David Garcia Balbuena. He did that thesis in 2015. And this is the most important donator of the metals into a set of veins here with silver, copper, zinc, lead, bismuth, and molybdenum. We cannot understand why, but the sad thing is that indium is missing here. We thought first it was something wrong in the laboratory that day or whatever, but it's something here that this evolved granite is very capable in producing these metals, often in percent grades, but the indium contents are in just a few ppms. Nevertheless, perfect example of hydrothermal veins related to a late phase granite. Next candidate is up here, where we have a small Rappakivi system, where the big coarse grained Rappakivi looks like that on the map. And then you have a very small little end of it, like a fingertip. And that little end, that is the interesting thing from an indium point of view. So if you look at that one in enlargement, it looks like this. Oops. It's just a few kilometers in diameter, but that is full of the blue lines I put symbolically in here. They are Grayson veins with reasonably high copper, zinc, tin, and sometimes very high indium grades. The highest indium grades are actually on a vein sitting there in the Svecofennian metamorphosed crust. It's a cutting vein, probably revealing another Pluton of this kind. So in that case, another student of mine, Thomas Pere, identified 570 ppm indium there, and not rockysite. This time it was the petrokite. That one I have not even learned to formula on, but it's a copper, iron, zinc, tin, indium phase. So we have it almost everywhere as we had a Rappakivi vein, a Rappakivi system. And the last important case is when we go to the far, far east. This is the Salmi batholith, was once part of the Finnish territory, but due to the same aggression as we see today in Ukraine, the Russians were here already in 1939, 1940, and took it by the same combined political military way from Finland. So this is officially now in Russian territory, and it has been not without problems to get there and get material, but I managed to do that for a couple of years until the borders closed again. So we have done a lot of work there also with help of students, both from Finland and from St. Petersburg. We have for a long time relied on this geological map made by Otto Trystedt more than 100 years ago. Now we have come so far that we actually have a better map than what he did, but it took us a long time to improve such a good map. Nevertheless, you see everything important in this map. The batholith, Salmi batholith, is here in the northwestern part of the batholith. You have intrusions into Archean units. This is Archean units, and there, while this is Proterozoic units. It's a very complex Precambrian metamorphosed complex into which the Salmi batholith intrudes. Parts of these Proterozoic formations going around the Archean areas, they have limestone. So we have limestones here, we have limestones there, and we have it up there also. And whenever this Salmi granite has intruded into this metamorphosed complex, fluids, when they meet the limestone, have a perfect trap there. So everywhere where you are closer than 2-3 kilometers from the intrusive margin and you are in a limestone, you get fantastic skarn formations. So when Trystedt did his map, this was an active mining region from here in the south up to here in the north, more than 20 kilometers of several mines that were producing iron from magnetite, zinc from sphalerite, tin from cassiterite, copper, silver, etc., etc. It was fantastic mining community that unfortunately had to close down even 100 years ago. Later, this scientist Vernadsky, just when the mines had closed down, Vernadsky is here and finds the indium. Well, it would not have helped much if Vernadsky had found it when the mines were operating, because when he found it, indium had no value. But this is the site where indium was discovered by Vernadsky in 1911. So that's an interesting area where we have the relation with the Salmi batholith. That's already said enough. This is how it looks into detail, where this is the Archean, this is the supercrustal limestone bearing sequence, and the mines are all over the place. not the least in this area, Pitkärantain, which is rather famous in the Finnish-Russian mining story. My PhD student, Mira Valkama, her name is there. She could confirm Vernadsky's discovery. And Mira could also do what Vernadsky and later people have not done. She found the rocky site also here in Pitkärantain. So Mira was first to identify it in Sundblad, and she was also first to find it, the real proper rocky site in Pitkärantain. And here you can see the grades. You can go from anything from about 100 up to even 600 ppm indium, and you have very nice silver content, locally some tungsten, tin, etc. So it was not bad quality that they mined, even if it was unknown what the indium existed. Some last words now about from where the metals come. We know where they are sitting, in the veins, in the skarn, etc. But people have thought that it comes from Rapakivis for a long time. But to really get the picture of it, we had to remap the area both at Sundblad and in Pitkärantain Salmi area. So this is a map we did on the Sundblad system, which was very simple before we arrived there. Before we arrived, it was simply only red color for the Rapakivi and a brown color for the Svecofennian. A rather good border between the Svecofennian and the Rapakivi, but we have found several types of Rapakivi. This is one type. This is another type in yellow, and this is a third type in light brown. And of course, this is the classical Viborgite. All the blue, they are veins we found in this project. This is the so-called Korsvik system with the extreme indium contents. We have other lead veins here. We have tin, copper, arsenic, molybdenum, bismuth in this yellow zone, and we have plenty of other types here. This is what we are now working on, the sulfur isotopes on this one. And as soon as you do proper mapping in areas like this, we can identify several granites belonging to the Rapakivi system. And the more evolved they are, like in this case, we call it Marviken granite, the more evolved they are, then they are the most metal fertile. We have done the same thing in Russia, where we also now see an improved version of Trusted's map. We have a batholith case here, but when you go into the darker red, they are more evolved. And what is maybe not easy to see in this map now, there are some extremely light red things there and there. Then they are very evolved rocks. So we can see in the mapping, the grain size decrease. We can see in the microscope also exactly how the mineralogy changes, and not the least in the geochemistry. By selecting certain elements, we can take this classical diagram from the Egypt team, El Boussaili and El Sakkari. That's quite a time since it was published, but extremely useful for Rapakivi studies. Strontium, barium, rubidium were normal granites in their terminology. Here we find the normal batholith character in black symbols here. But as soon as we get into more and more mappable evolved granites, they have much higher rubidium contents versus the barium. So these are the red, they are the first evolved type. Into the green, extremely more evolved, until we have the absolutely crazy rubidium contents and almost no barium at all. That's an evolution trend that we have investigated more and more by looking at the barium rubidium ratio. See that it's the same thing when you look at zirconium and hafnium. So we have developed a new diagram where we put the rubidium barium ratio here. In principle, when looking here, It's the same thing like going in this triangular diagram, but we now also put the zirconium hafnium. So all things we saw in this picture. Black symbols for the non-fractionated granites, red for the more fractionated, green and blue. Remember that, black, red, green, blue. That goes into this diagram combined with zirconium, hafnium, and rubidium barium, that the black symbols are up here, go down to the red population, green population, into the blue population, and these are extremely fractionated, very ore fertile. We can also look at the rare earth pattern. The black symbols are giving quite a marked europium anomaly, and otherwise rather flat diagrams. But the more evolved we get, the red symbols, the blue symbols, and red, green, and the blue, the diagrams get more and more flat in general, and the europium anomaly gets crazy low. I've never seen so low europium anomalies as we have in the Salmi most evolved phase. So this diagram, that diagram, and the triangular diagram with rubidium, barium, strontium are some of our thermometers of getting a good indium fertile granite. And this is how it can look in the field when it is really exposed. This is from a quarry where we have this most evolved granite down here. Up here, the dark is amphibolites of Archean age. So the granite here intrudes into the Archean rock, and it creates a 2-meter wide front, is maybe the best word I can use. And that front is what is in German called Stockscheider pegmatite, extremely coarse-grained quartz, K-feldspar, biotite granite, extremely evolved. And this is a classical phenomenon for many rapakivis. When they intrude into an older rock, they produce this front of Stockscheider pegmatites, very visible in this quarry. So now, finally, we get to some conclusion of all this, that we can see an indium-rich metallogenetic belt from western part of Svecofennian through the Åland Islands, southern Finland, all the way into Russian Karelia at Lake Ladoga. They are always related to continental rift style of granites, and they are not part of any previous mining district. So the age situation is much younger than normal ore deposits in Fennoscandia. High indium grades are very, very often related with high zinc grades, and that's why we normally find indium inside the sphalerite. But in rare cases, like we have in this Korsvik case in Sarvlaksviken, we get those fantastic rockosites because we have very little zinc here. It's too little zinc to produce meaningful amounts of sphalerite. So indium simply has to go somewhere else, and rockosite is the best solution for it there. And the most promising, best targets we have is, first of all, Salmi batholith. That's where they have sizes, ore grades. The second best, I would say, is Sarvlaksviken, where we definitely have the grades, but so far not the sizes. I think that's more than I could press into in 40 minutes.
Okay, after this 40 minutes presentation, if anyone has any question.
Thank you for your presentation. I understand that those mineralizations within the skarns are related to the batholiths, but those in the veins cutting the granites could be related to more younger events, or they are related instead to later stages of recrystallization.
When I say late events, I mean part of the Rappakivi story. When we are dating, which we have done, really dating the different generations. Let's see here. That batholith granite in here, 1539. When we go here into that 1538, the very highly evolved rocks, 1535. We are in few millions. Very difficult to say if it is really detectable with the precision of ±2-3 million years. This is the range. We are definitely inside a single magmatic event for this, even if it's getting progressively smaller grain sizes, and not the least this geochemical trend that we see in these diagrams. So we go from the primitive rocks into the evolved very quickly. And all the metallic concentrations, they are derived from this sort of generation. Phase is maybe the better word, a phase than a generation, because it's not a long time. It is a continuous process of the magma evolvement from proper magmatic into a magmatic hydrothermal situation.
Thank you.
All right, anyone else? Okay, thank you very much, Professor Krister Sundblad, for this interesting talk. He's going to be around at the Faculty of Earth Sciences until the end of this week. So if anyone else is interested to meet him and talk to him, so he will be available.